All right. Let's go back to where we were last week. And actually, I made a lot of progress since last week. So we were building a Shazam clone with self-supervised learning using the SimCLR model. So the idea is very simple. Do I have it here? No, I don't. So let's look at it. Where is it? Nope. Yeah, here. Simple framework for contrastive learning of visual representation. The idea is basically, let me zoom in, that you start off with some image X and you sample two random transformation, T and T prime, from a set of different transformations. These transformations could be adding blur or like changing the colors, rotations or whatever. And so you sample these two transformations and you apply them to your image X, and that results in two different images, X tilde I and X tilde J. You then pass these two transformed images into an encoder F, which is in this case a ResNet 50, I think, which gives you a vector H, so two vectors, Hi and Hj, which you then pass into this projection function G, which is a simple MLP, and so it returns this vector Z, I and Zj, which are two projections. And then the goal is to use a contrastive loss to maximize the cosine similarity of these two vectors, because at the end of the day, they correspond to the same image. So you want to learn F and G so that the output, the two projections output of the model, are very close together, i.e. they have a high cosine similarity. Anyway, so we did that, and so as you see, it's pretty basic. Now, in our case, we're doing this on audio, so we have our input not as an image but as a signal. So what I do here is that I transform this signal into a spectrogram so that I can have an image that I can feed into this SimCLR model. And the second challenge is for the transformation. It doesn't really make sense for me to rotate the image because the sound is not going to have any meaningful like representation if I rotate it 180 degrees. So instead I have a bunch of different transformations. So what I do is that I use this SOX library that is implemented in Torch Audio to use a low-pass filter to change the playback speed, which I also have here, so I should probably remove it from there. I just changed the rate, and actually I'm not changing the rate, it's just that if you change the playback speed, the sampling rate is going to be different, and so you need to resample to keep the same sample rate in the output. And then you can add reverberation, and that's pretty much it for now. I'm gonna have to add some more. I had a background noise as well, but I just realized that it's behaving weirdly, so I just removed it as of now. Anyway, that's the data set. This is the model, and it's work. And for the model, as we said, very simple. I have a first convolutional layer because my input is different from ResNet 34. So I have a first conv layer. Then I use a pre-trained ResNet for F. Where is it? Here, F is my ResNet 38. And then I have, so I just change the fully connected layer of the ResNet to change the output dimension. This is my hidden dimension. This is the size of vector H. And then the final projection, which is G, here, that takes 1024 as the input dimension and outputs a vector Z of size 124. Very simple, very, very simple. The tricky part is actually later on. So this is the loss that we're using. This loss is called Normalized Temperature Scaled Cross Entropy, NTXNet. It's not that hard, but basically it's a cross entropy where you have here a pair of positives. So Zi and Zj are here, Zi and Zj, and then you divide it by the sum of the negative pairs. So the Zk is coming from a different input image X. Anyway, so in your batch, instead of just n samples, you have 2n because you duplicated the input image. So this is the implementation of NTXN. I don't know how to call that loss, but anyway, last week my implementation didn't work, and I found this on Lightning PyTorch examples. They have, I think, somewhere here. I think I can do this. Yes. If I look for SimCLR, can probably find something. Nope. Let's see. Models. Self-supervised here, SimCLR. So they have a cool implementation here. A bit complicated, but I was able to find the implementation of the loss here that I had to update a little bit so it works with my implementation, and it works fine. So I've just tested it here with some dummy data, and it does output. So this is the expected output, and this is the output of the function. So it does match, it does work. Perfect. Then I'm evaluating the model. I'm cheating a little bit here because I'm using my test data is the same as my training data. This is bad, but this is quick and dirty prototyping, so it's okay. What I'm using as metric is recall at k, which means that I'm looking if the predicted song is equal. Like, let me go back. My model is gonna output the array of all the songs from the library, ordered by best match to worst match. And the recall at k is just counting how many of these predictions had the right one as the first element, how many of these predictions had the right one in the two first elements, and so on and so forth. You get the idea. So I'm computing this and I'm building the catalog. So what is this? I'm just taking my library of songs. I'm feeding them to the model so I can get a set of vectors z for each of my songs x, and then I'm saving them. So I have songs. These are the titles of the songs, of the waveform. This is the audio signal of the song, and index is the z representation, projection of that song. And then what I'm doing when I evaluate that is that I'm just taking the, oh, by the way, here I need to normalize that. So I'm going to say normalize features. So here when I'm doing, let me just fix this. Sorry for that. Beam similarities. Okay, cool. So I'm computing the similarities by just taking the dot product of the features and the catalog index, not features. Is that correct? It sounds right. Oh, but I'm not using that function actually. I'm using fake evaluation. So let's delete that one. So my evaluation, what I'm doing is that I just, and I'm gonna remove this and iter to do it just once. Okay. So basically I'm computing the cosine similarity, so the dot product, but where the vectors have been normalized. So I'm just computing the angle between these two vectors to find the best matches, and then I'm returning this array, and then I'm computing recall at k. Anyway, it's pretty standard. And then this I'm gonna remove, boom. And then what I'm doing is that I'm just training a normal training loop in PyTorch. So optimizer 0 grad, feed forward, compute loss, loss.backward, optimizer step, and track the loss. Pretty basic. Now another addition since last week is the use of Lars, which is apparently another optimizer different from the usual SGD and Atom. Haven't looked at it yet. Again, got it from PyTorch Lightning. This is the one used in the paper SimCLR. I've used the same hyperparameters described in the paper, and look at that. This is training like crazy. The loss is converging to 0, and recall at k is 1 everywhere. What does that mean? It means that it's always predicting the song and putting it at the first position. How awesome is that? Now, we have a model. It's running. It's perfect. Everything is good. We want to run this in production. And to do that, I had a problem with previous projects, which is you can't just, you can use PyTorch in production, but it's very, very big, and usually you would need like several gigabyte instance to run Inference in production, which is expensive. So what I want to try now is using ONNX. So ONNX runtime is, what is it? That's a good question. It's basically a framework that you can use, where you can use models imported from PyTorch, TensorFlow, whatever, and run them. So it's not for training, it's just for inference, I believe. And I think, I would guess that it's pretty lightweight because you can use it, you can use it in the browser. So I guess it's lightweight, so I'm trying to do that. I'm gonna build a handler function with Python that is gonna be deployed on AWS Lambda using ONNX. So my ID is that I'm gonna have here, handler is gonna take a request. I'm gonna get the audio from the request, whatever, I don't know how it's gonna work. I'm gonna process that audio to get the spectrogram. No, actually, I'm just gonna say like predictions, inference of audio, and then return a JSON object of the predictions. That's what I want to do. This inference function that takes an audio, I guess, would have to say something like get sample from audio. This would return a signal in a sample rate. Then it would say get the spectrogram from that thing. And then projection model spectrogram. So I'm running the model on the spectrogram from the audio, which gives me a projection vector. And then I'm gonna say max inner, so find best match with projection and library or catalog. Let's call it library. But first I'm gonna say library equal load library. And this gives me best match. And then I can return best match. That's the idea of what we want to do. Now, this model is going to be model load model. It's going to need a file path, right? It's not like model.pt, .onNX, sorry. That's the idea, right? Oof, what's going on? Cool. So let's build just that. The first step is to actually get that. Oof, shit. The first step is to actually get that file model.onNX, and to do that we need to export our model using the ONNX extension, and this is pretty tricky, but I think PyTorch has a great documentation, better than the ONNX one. Cool. So the way it works, yes. Yeah, so the way it works is that you call torch.onNX.export on your model on some dummy input just to inform the ONNX format of what is the expected shape of the input, a file name for the output, and input names, because you're gonna give it as a dictionary or a JSON object. And output names, this is so that here, when we're gonna get the output of our model, when we run inference, it's actually gonna be output and then whatever the name of the output we gave. So it could be like projection, whatever. You get the idea. So let's see how that would look like for our example. So we have a model. Yes. And we have a data set, right? Oosh. Should have not said that. Let me go back here and copy and paste that in here. This is... I don't have dynamic input, so I'm going to remove that. This is cool for NLP, but not for me. The model output's name, yeah, let's keep it as output. Input names, I have just input. Do constant folding. I don't know what this is. Upset version. I just want the default value for that. Export params. Store the trained parameter weights inside the model file. Yeah, of course. And then I'm gonna call this SimCLR with date time dot now. Let's see how this would work. Of course, it doesn't work because we are missing the final closing little stuff. Cool. And for next time, let's add verbose true to see what it says. Okay, if I reload this, I should have now SimCLR. Oh yes, there's nothing like this. Cool. Oh, it's not giving me a timestamp. Timestamp. Method, yeah. Oh, I need date time dot now dot timestamp. I guess. Is this what I need to do? Yes. But there's a dot. You know what? I'm just gonna say def or lambda now. This function now. No, yeah, this is what I need. Lambda function that returns this dot split dot and takes just the beginning. Now, if I call now, object has no attribute split. Oh yeah. Maybe I can just say int. Why not? Yes, cool. So let's do that. All right. And for next time, I'm gonna put it here. Let's delete this. Yes. And let's delete this one as well. And do it again. Now up and up. And we're gonna see the verbose true. Oof. Actually, I don't want it. Sorry, my bad. We don't want verbose. Cool. So if I reload that bad boy, we should have that. Let's download it. Ooh. Is it that heavy? I hope it's not. Model path. Okay, so how is it gonna work? Let's say here if name equal main. Okay. I'm not sure what will be the not sure how I'm gonna get the audio on the API side in the handler. It's either gonna be I think it's gonna be like a base 64 thing. Not sure though. Anyway. Yeah, let's save it here for now. And this is gonna be copy path. And let's say that, just that's enough. And here I'm gonna say model path. Cool. Model path. All right. Now let's see how inference assets. Okay, I'm gonna have a lot of things to do actually. But anyway, assets, test. Let's create a new file, .init.py. I don't know if this is gonna do it. New file, init.py. Name, test, samples. Okay. Triple equal doesn't exist in Python. Test samples and whatever. I don't know what I'm gonna try here. And then model path is whatever. This is gonna get me the best match. And then I want just to print best match, I guess. Cool. So let's see first how to load. Let's close these. Let's do everything in one file for now. Let's see how we can load a model from a model path with ONNX. So I have my exported model. Now I want to load. I want to create an inference session. So I don't care about loading the model, because see, you can either load the model or you can run inference without even loading a model. So I don't care about loading the model. I just want to do that actually. So let's update that to say something like this. These are gonna go here. This is our model path. And this is gonna be our spectrogram. .numpy. Why? Text. What is text? I think it's just a subtle way of telling us that this needs to be a NumPy array. Because look, torch.tensor.numpy. That's great because I'm not using PyTorch. But that also means that my spectrogram is going to get built with something else than PyTorch. Actually, maybe I can use Torch Audio without... yeah, actually, it's okay if I use Torch Audio. I believe. So let's install that. Let's install that bad boy. I hope it's not going to be super heavy. Oof. 100 megabytes. That is heavy as fuck. Okay. Anyway. Oh yeah, this is... this needs to match the way we called our inputs. So let's call this input. I should have called it spectrogram. So let's change that. Okay. Then we're gonna get outputs and output names. I don't understand why it doesn't use the output names. Output names output. Apparently you don't need that. Argmax. So our model is gonna print us projections. So let's call that projection. The next step is gonna be to do the cosine similarity against our library. So the way it works is that I have a library. My library is, let's do this, okay? The library is I'm gonna save it as a JSON object maybe, and it's gonna have title. This is an array of all the titles. It's gonna have, oh, actually, no, yeah, title, waveform, again, an array of arrays. Cool. And the most important one is the index, or should I call it projection? Let's call it index. And this is going to be, again, arrays. Okay, cool. This is the library. Now what I want to do is, as I'm doing somewhere here, this is what I want to do. Okay. I want to, I think there's a NumPy norm. Yeah, you can just do that. Okay, yeah. This is the way to go about it. So basically, I'm gonna have to say projection divided by np.linalg.norm projection. Okay. And library, take the index. So I'm going to get that. I can just use the at, I think. This is a new Python symbol for matrix multiplication. Transpose, I don't know if... what is matrix.transpose? .t, cool. I can use .t. Perfect. And then once I have these similarities, I can say similarities.argsort. Let's check argsort. Yep. And I can say order none. Oh, I cannot. I don't understand. What is this order thing? D type X, Y. What? D type? What is that? Sort, describe sorting algorithm used. Oh. I don't know. No, I want the arg sort. It can be a string. NumPy array arg sort reverse. It's always possible. Just gotta do it. Some weird manipulations. If you negate an array, the lowest elements become, yeah, of course you can do that. Another way to reason about this. Okay, I'm good enough with this. So let's do that. This minus alg sort, boom, and then n to get the n. I want all of them for now. And then I don't need that. I can just say flatten. By the way, here, I'm gonna say flatten here. So I can say sorted index. Here I'm gonna call it title. And then I'm gonna return sorted songs. That's going outside here. And here it's the library. Cool. Now the library is going to be load library. Library.json. Yeah, there's a JSON library that tells you, yeah. That's how you do that. So basically right now I have a catalog that looks like this with some arrays or whatever. Just checking the shapes, yeah. So what I can do is this. So I have a catalog. This is my catalog. Catalog library JSON. catalog. Let's see if it's gonna work. Can't you specify a name? Oh yeah, this is how you do that. Actually, cool. So you need to say library.json and say this, and then dump catalog and JSON file like this. All right, let's try it. Of course, it doesn't work. Takes one positional argument, but two were given. Yes, indeed. Dump. Is it just that? No. It was actually of type ND array is not JSON serializable. Okay. What I need to do is change this a little bit. So catalog is that. How about if I say library equal copy or dot copy? Yeah, works. And I'm gonna say library of song equal library song dot to list. I think you can do that. Yeah. Now say library of waveform equal library of waveform dot to list. Yeah. And then library of index equal library. I don't think I can just do to list. Maybe I can. I can. What do I get? Oof. Of course. What the fuck is that? What is that? Okay. Let's hope it's good and delete that. Try again. This is temporary. We cannot do that with like thousands of songs, but we'll say it's good enough for now. Let's download that bad boy. And we'll be able to load that from here. So import JSON, JSON load Python, JSON.load. How about that? Okay, this is just how you do that. So my load library function is just going to be that load library, library file path. It's going to be with open file path, read only as F. Okay, diva source, yeah. As F, we're gonna do this. Nope, not that. This here. JSON.load F. Data, its library, and then return library. Just that. Simple, right? Cool. So here I can say load library. I have my library here. And then I can say similarities and whatnot. Now we need the processing. Let's get started with some audio file path for now. All I want actually is this audio file path. Okay. So let's say get spectrogram from file path. This is what I want. Okay. How on earth am I gonna do that? I have no idea. Oh, actually, I do have an idea. I've downloaded Torch Audio, so I can just do that with Torch Audio. So let's see. Get sample is just doing that. Import Torch Audio. So Torch Audio is loading the file path to give us the waveform and the sample rate. Preprocess signal is doing what? It is doing a bunch of stuff to resample and whatnot. Let's use it actually as it is. So I'm going to say preprocess signal. Let's remove that. Let's call, yeah. Okay, and it's going to have a target sample rate as well, which is going to be equal to, let me see, this. All right, and then np.mean. NumPy mean keep dimensions. Can I do that? Yes. Keep themes. And dimension equals 0. All right. Num samples. It's going to be just adding a 0 here, right? Yep. And then pad. NumPy pad. It exists. How awesome is that? So I can just say np.pad. Is that true? I think it is. Pad width sequence array like before and after. Let's see. All right, so I have this preprocess signal thing that takes a sample rate. Wait a second. Do I have an error here? I'm saying sample rate here. Oh no, okay. This is not signal, this is waveform. Okay, get spectrogram. This is the point. I cannot just say get spectrogram. That's the function. How am I getting these? Oh, yes. This right there. Boom. So spectrogram is this with target sample rate equal to, oops, this. So I can actually say here target sample rate right, and then waveform. Cool. All right, sounds good. Let's give it a try. So I'm gonna say assets, test samples, and let's take test clip, download. Let's actually put it here. It's gonna be easier. Let's say test clip dot wav, and it should print everything. Let's see. Moment of truth. I'm gonna say Python source handler dot py. How bad is it gonna be? No audio input output available. I think in storage audio, right? No audio backend is available. What does this mean? Torch audio, no audio backend is available. Okay, sounds good enough. Let's try again. All right, error opening system error. Okay, let's go to handler. No, source, sorry, and Python handler.py. All right. Input got 3, expected 4. Please fix either the inputs or the model. Okay. I think I have some problems with this or that. So let's see. Print spectrogram.shape. Did it work? Remove that. Oh, torch. Why? Oh, it installed torch. Fuck. 164 43 431. Got 3, expected 4. Please fix either the inputs or the model. All right. How about if I say dot and squeeze 0 dot numpy. List attribute doesn't have a T in it. Yes, because I need to say np.array of that. TR title. It's called song. Only integer scalar arrays can be converted to a scalar. Yes. So I need to say this np array. Okay. It works. It works. And this is in fact say so. Amazing. Amazing. But we are using PyTorch, I believe. Let's see. NumPy and squeeze. Expand dims. Okay. So I can just say expand dims 0. Yes. I need to change a few things. So right now, I think like if I say, let's say I were to say, how is it again? Pip requirements. I think it's like pip freeze, right? No, pip freeze. Yes, like this. Pip freeze requirements dot text. Oh, it put it here. We have Torch, yeah, and Torch audio. This is bad because if you look here in there, this right here, properties, 1 gigabytes. 1 gigabytes. Do you see that? And if I just select these, this is a gigabyte as well without the assets. This is because of PyTorch. So now we need to get rid of these two. So let's see how we can do that. Where are we using Torch audio? We are using it to resample and to load the file, but we can do it without it. Let's see how. First, we can load stuff with Librosa. So let's import Librosa. And I think we can do a lot of things with it. Let's see if we can Librosa mel spectrogram. Yes, we can. How does it work? Let's hope it works exactly as that. So I'm gonna say librosa.feature.mel spectrogram. The first item, audio time series, and FFT. Okay. The first is gonna be my waveform, like that, and it's gonna return a NumPy array. So pip install. Yeah, so I'm gonna say pip and install torch audio. Yes. Yes. Okay, and pip install Librosa. I love these new progress bars. Colorful, modern. Cool. Now let's see if our project is lighter. See, not even 500 megabytes. How crazy is that? But it has to work. So let's see if it works. Have Librosa, resample. So we want Librosa resample. Of course it has resample. Can we give us, we give it a signal, and it returns a signal with the right original sampling rate and target sampling rate. Yep, it works just as expected. And we can go about it as we would with Deutsch Audio. Let's see if it's gonna work. Okay. Python handler.py. Oof, 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 oof. What is going on? Nope. Min got an unexpected keyword argument. Dim axis. In NumPy, it is called axis and not dim. I think I can just say 0. But wow, it took a while. Oof. Tuple index out of range. Okay. What is that? Tuple index out of range. Oh, I think that maybe this will return resample times. Oh, maybe this returns two stuff. Y hat and Librosa load resample dot shape. Oh, returns an array like this, actually. Okay. So we've resampled it, but this is doing something weird. So I need to first do that. I need to first mix the different channels to make sure it is not weird. Actually, you know what? I'm going to say Librosa load. I'm going to print waveform dot shape. Okay. To make sure it's loading the different channels. Okay. There's only one channel. Why not? Why not? I don't like that. But hey. Cool. this. Okay, so signal here as given by process signal, preprocess. I'm just gonna say preprocess. Is giving us a signal that has only one. This is just an array. This is just a simple list, okay? And not a list. This is an NumPy array with one dimension. So here I'm gonna need to expand it more than just once, I believe. But let's see. Malloc got an unexpected keyword argument sampler rate. Librosa Mel spectrogram. S is spectrogram sampling rate. This is SR, not sample rate. Hop length and nmels. There's no such thing as nmels. So how do you specify the number of mels you want? Oh no, I can do that. Nmels, cool. Let's try again. All right. Object has no attribute. Expand dims. Oh, it does. NumPy and squeeze. Expand dims. Oh, maybe I need to say np dot expand dims. Like that. Right. Let's try again. Okay. I need to do it twice. How about if I say 0 and 1? Okay. Boom! There you go. We got that. All right. So let's commit this. .json. Okay. I'm gonna go to .getignore, and I'm gonna add here that I don't want anything that is .json. And I want anything that does look like an ONNX model, and anything that is a WAV as well. Cool. And let's remove this init for now. Oops. Cool. Very cool. Utils model. We haven't got anything yet in here. Oops, no, not the handler. Delete the file, yes. Data, you can delete the file as well. We just want the handler. Yes, and the requirements, let's do it again. Pip freeze requirements.txt. If we look at it, we have ONNX runtime, but we don't have torch audio or torch cool. So we can add that, and add that. And I'm gonna say, ta-da, fit running inference with ONNX without torch. And let's see the changes. Cool. Now, what we want to do is go to a handler, and we are not going to... Actually, you know what? I have a GitHub repo. It's called Speak Fluent, I think. Nope. Let's see. Speak Fluent model. Yes. Oh no. Speak Fluent. REST API. Oh, right. So in this, I did I had a function, a handler that was taking an audio like that. So you get a request. So the handler is actually getting a request like this. That's right. That's what I was saying. And what it does is it gets it from a form. So let's do that. Request.form.audio. .get audio. Oops. And file name. Okay. So this is the file. File name equal this. Oops. All right. And then I was saving the file locally, which is a bad idea, but hey. And then I was saying word, get word, and then I can just do the whole thing. But at the end, I can say JSONify, but this is specific to that, so I don't care. And then I can just say inference or run inference. No, inference like this. Inference, it takes what? It takes an audio file path. So I'm going to say file name. It takes a model path, which is already set. And it's going to return the best match already, right? No sorted songs. Oosh. All right. If I just do that, no. Source Python handler .py. So this is just returning an array. So let's say okay. Song best match titles, and then titles best match titles, and then later on I might do something like song URI and return the URI for an S3 bucket, whatever. And that's Oh yeah, and I want to return also like match percentage. And it's gonna say to the user like, here is the best match, but it's only like 20% or something. And I do have that already, but okay, cool. Looks good. Let's take a break and come back to build an actual handler that will be able to upload and deploy to an AWS Lambda function. Be right back. All right, so let's figure out how we can go from this little script right here to a handler on AWS Lambda. A while ago, I created this tutorial on how to do exactly that, but I was using PyTorch and Docker. So let's just get to the part where I build the Lambda handler. Okay. So what we got here is a Lambda handler takes an event and not a request. It's pretty much the same thing, I believe. And the event is gonna have a form, I guess. Yeah. And I'm gonna get from this event, from the form, I'm gonna get the audio part of it. This is gonna be the ID, or like recording. Like this is because on the front end, I'm gonna have a form like this, and I'm gonna have a input of type audio, I believe, ID recording. That's the ID, right? Input HTML audio. Oh, okay. I see. It's like that, actually. So it's going to be a bit tricky, but audio, and I'm accepting WAV, nothing else. And basically on the front end stuff, I'll have to do, I'll have to create a recording button, and then once the recording is done, I'll have a JavaScript function that is going to create a file and automatically upload the file. So this is going to be, all of this is going to be hidden. And this JavaScript function that creates the file, audio file, is going to submit the form as well with this hidden. So all of this form right here is actually going to be hidden. It's not going to be a typical form as you might expect it. Anyway, and this is going to have the ID recording. So I get the file, I get the file name, I just add WAV to it. I'll print the file, and I save the file. Why? I don't know. I just do that. Maybe I shouldn't. Anyway, now that I have the file in my directory, I can call the inference on that file, and everything works as before. Now, status code. Okay. I'm not just returning this, I'm returning status code 200 and a body. Oops. Like that. Is that correct? JSON.dumps. Okay. I think I can just do that, actually. Oh, ONNX inference with Python in AWS. Look at that. This is exactly what we need. Cool. ONNX runtime and Lambda. First, download your Lambda deployment package from the AWS portal. Your Lambda actions export function deployment package. Yeah, see, that's the thing. I believe it's better if I use a base 64 encoding of the audio instead of a file. So basically on the front end, I'll have not this, but that, like audio equal event dot body dot get recording, and then I'll have a base 64 dot decode of audio. That would be cleaner. Yes. Here you go. 5. Let's check the repo. Wow. What is respond? API response. Let's oops. I hate that. So I'm gonna have to upload my function to S3. It's kind of annoying, but hey, whatever. So if I go to functions, can I create a new one? Author from scratch. I don't want an image. I want Python. Yeah, Python 3.9. What is difference? I think our ARM is better. By the way, Diva is the name of this project, which is pretty bad, as always. Handler. Let's create a function and see how it goes. All right. Ooh. I'm tempted to do something very, very nasty, which is upload the files directly here. let's try that. Can I upload stuff in here? Go tools, environment, file. Or is there a terminal I can use or something like that? Fresh file. Show hidden files and folders. Upload from Amazon zip file. Upload. Oh, okay. I can upload a zip file from the, oops. I can, what's it gonna do if I test? And the output is this. Cool. Wow, you want to bill me for this? Dude, chill. This is just a test. Can I change that event to format JSON? No. Function overview. Add a trigger. S3, no. Cancel. Configuration maybe. I might need more than just that for the memory. I'm afraid. But we'll see that later. Have environment variables. destinations. And then we have the code here. This is the execution results. Okay, I don't really care. And then we have this test event. Okay, can I try edit saved events, create new event, test event, Lex, book car, common. What's that? Records, request, get, client IP, user agent. Wow. Nope. What I was hoping to get is something like this, recording. And then here, I guess I'll have a base 64 audio recording. How does it look like? Oh, I can pick a file. I guess that's what I want. Okay, cool. Wow, that's big. But that's ultimately what I want, right? This big ol' JSON file is what I want. So I'm gonna say copy. This is gonna hurt. Oof. Yes. Just like that. I'm not gonna click format JSON because it's gonna break. Okay. Audio, mime, and data. Cool. Maybe I could, yeah. Okay. I'm gonna say save. Oof. Yeah, it worked. Now here, package size 299 byte. I would like to do this, honestly. But, sorry. So I'm gonna remove that. And the way it's gonna work is that this is gonna be the Lambda handler. So I can context. So I can remove this, right? Boom. There you go. but it doesn't work like that. I need to install these stuff, and apparently there is a way. ONNX, AWS, Lambda. I think it was here. Yeah, it's here. How do you upload stuff? Okay, first download your Lambda deployment package from the AWS portal. Your Lambda actions export function can do that. Your Lambda actions. I think he meant functions, right? And then export function. Can I export? Oh, yeah. Actions. Yes. Export function. Okay, so I can do that. Next, you'll need to pip install on a Linux machine. It's important to compile this in a similar environment to what runs in a Lambda to avoid any compatibility issues. After installing, go ahead and find the ONNX runtime folder under your Python env lib Python 3.x and copy that to your deployment package. What? Oh. Basically what you do here, which is kind of nasty, is that you come here, you go to lib, site packages, and you come here and get all of what you need. For real? And you put that where? It's kind of nasty. And then what? Then you decode this. Oh, yeah, in fact, that's what he's done. Cool. Okay, yeah. This is a bit nasty. Basically, you use these dependencies as if they were just here. So all the dependencies that I'm using here, you want me to just put them here. So if you go to Google, protobuf, then there's everything in here. Man, that's not a way of doing it. Doesn't sound right. Librosa. Okay, so you want me to say basically Librosa, ONNX runtime. What else do we have? SciPy, I guess. Scikit-learn? No. What else? Google. Yeah, that's pretty much it. You want me to do that? I don't like that. How heavy is that? If you just look at this, yeah, just this. Oof, 200 megabytes. Yeah, but this source has the library and the model, which are pretty big. Like if I don't look at the source and just that. Yeah, what is the big one? I think I would bet it's Librosa. 1 megabyte. ONNX runtime, of course. 16. What? How is that possible? Oof. No way. SciPy? SciPy is that big? NumPy.libs. Oh man. I'm tired. I'm gonna have to do a little bit more Googling. But here is the idea. Let's clean that. Here is the idea. These are things I'm gonna have to do for the model, but forget about it. What we have to do now is create a Lambda handler as lightweight as possible. Figure out how to deploy it to AWS Lambda. Do we need to store it in S3? I think we do, because it is larger than 50 megabytes. This is the limit, apparently. The next thing is update the processing function to take a base 64 audio object instead of a file. I don't know how to do that. Like, here, right? No, not there. Here, like the browser load file path. Maybe we can find that actually. I say the browser load base 64. File like object. What does that mean? What does that mean? Path to the input file. Any codec supported by sound file or audio read will work. Any string file paths for any object implementing Python's file interface are supported as path. If the codec is supported by sound file, then path can also be an open file descriptor. So I want to see if sound file read bytes. Let's see. I think I can just do that, actually. I think I can just do that. So I said B64. Is that the same thing? B64 decode. Yeah. So audio is going to be the encoded string. Encode string. And I'm not even going to bother with all of that. I'm directly going to say encode string. Encoded string with a D is going to be better. I think this should work. Actually, we can try it, right? So how about if we test that? I'm going to save this. Okay. Encoded string. Oop. And here I'm going to have encoded string. And this is going to be my test clip. Read. Okay, cool. Let's see if it's working. Python handler.py. Ooh. What is that? Am I printing this? No, I'm not. Why are you doing that then? Let's see why it's doing that. I believe it's freaking out. Dude, what are you doing? I don't understand why you are doing that. Oh, mate. Dude, what is that? Oh, supplied file names too long. Yep. Alright. Alright. Space. The browser load base 64. This looks like a notebook. How to load web file. Nope. Path to the input file. This can be any object implementing Python's file. Yeah, file like object. Oh, by file like object, I think they mean something like a pathlib.path instance, but not a base 64 path type of thing. So I believe we are gonna have to still do that. Up. I think we're gonna have to do this weird stuff here of decoding and then encoding and then decoding and encoding again, which is a bit of a bummer, but why not? So this is gonna take a file name and the encoded string is going to be, oh yeah, I need to do that. Base 64 code audio. I do want to do that. No, this is not what I want. I got it. A few encode, decode. Shoo. Python. Some file read. Maybe that. Yes. So I'm gonna have to do that here. So basically, I'm gonna have to say with open temp web w is f, and then I'm gonna have to say that and that. So, oh no, I don't need that. So first we decode the encoded string. This is the encoded string. And then we say f.write decoded string. And then we can say, I'm gonna remove that and say best match titles of tempwav. Like that. Look at this. Yes, 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 yes. That's how it's gonna work. Actually, cool. All right, let's stop it here. I'm tired. I can't think anymore. So we said that we need to create the Lambda handler. update the processing function to take a base64 audio object instead of a file. Nope, we're not going to do that. Deploy to AWS Lambda and then test it with a base64 encoded WAV file in the body of the request. All right, this is going to be a post request. Cool. Let's see if we can do this week and deploy a prototype of that stuff. And yeah, hopefully we can have a little prototype